Hey Einsteins, and welcome to a new video series on the Wormhole channel. This series is going to be focused on getting you started with writing cross-chain code. Today, we're going to go over a very simple example of sending a message from one EVM chain to another, but in that process, we're going to help you set up your environment, go over where to find all of this code, and explore the documentation that's available to get you started. In the future, we'll expand on these examples by adding in more advanced payloads, token bridge payloads, and multiple ecosystem support like Solana and Cosmwasm. Let's take a look at the xDapp book and where to find all the code that we'll be interacting with today. If you navigate over to book.wormholenetwork.com, you'll be greeted with this page. This is the xDapp development book. It's a set of documentation to help you get started writing your first cross-chain programs. Not only does this cover how to write code for Wormhole, it also talks to you about why an engineer might want to go cross-chain. If you look on the left, some stuff is grayed out. This is stuff that we're still working on and will be ready shortly. If we scroll down to before you start, we'll learn how a Wormhole development environment is set up and what are the pieces that we need for it. In short, to get Wormhole up and running, we're going to need to first deploy the chains that we want to connect to. In our example today, we'll be running 2 EVM chains. Then we're going to need to deploy the Wormhole core contracts to those chains. Then we need to run something called a Wormhole Guardian or a Wormhole Validator that actually listens to the core contracts on those chains for emitted messages. And finally, we're going to deploy our own code to those chains that interacts with the Wormhole core contract. Now, all of this sounds like a lot, but we'll see some of the tools that we'll cover today that streamline this process. Today we'll be using Wormhole Local Validator, but in the future you might want to consider using Tilt, which is a full-fledged Kubernetes deployment that runs every chain connected to Wormhole. Wormhole Local Validator is a little bit easier to set up, but Tilt provides you with a synchronized and concise environment that is useful in production CI/CD deployment pipelines. So let's get started with Wormhole Local Validator. The first thing you need to do is go up to Introduction and click on this link, the GitHub repository for the xDapp book. This will have all of the code that we need under projects. So it's really important to go ahead and actually just clone this repository somewhere locally. I've already done that, so let's go over to that now. As you can see, I'm in the xDapp book folder. I can navigate into the projects directory and the Wormhole Local Validator directory. So the first thing we're going to do is deploy 2 EVM chains. These are going to mimic Ethereum and Binance Smart Chain on the mainnet. So they're going to be on Wormhole IDs 2 and 4 respectively. We can do that by just running one simple command in the Wormhole Local Validator directory called npm run evm. This is going to go ahead and set up those 2 chains using Ganache instances and then deploy the Wormhole code onto those chains. It uses something called PM2, which is a process manager you'll see Wormhole Local Validator use. And we'll talk about how to use PM2 to get logs and just to check that everything is working after it's deployed. Here we can see it deploying the Wormhole contracts onto that chain. This will take a little bit, so I'll probably skip ahead to when it's done. And we're almost done deploying this code. Now you'll see an error pop up here, invalid or verify value. That's totally fine and expected as long as you get the second, you get this WETH token deployed at 0xDD at the bottom, you're good to go. So again, this error doesn't really matter. Just make sure you have this WETH token deployed at 0xDDB address up here. Once that's good to go, let's clear this up. And now let's run Wormhole, or Wormhole Guardian. We can do that by doing npm run Wormhole. It'll just run the Guardian D instance, and we can check that everything is working by doing npx2 or npx pm2 list. This will just print out the 3 things that we have set up, EVM0, EVM1, and Guardian D. If we wanted to see the logs of any of these, we can do npx pm2 logs and then the name of the service. So if we wanted to check the logs for EVM0, we could do npx pm2 logs EVM0. You can see those are the current logs. If we wanted to see logs for EVM1, same thing. You can see the logs. And then if we wanted to see the logs for Guardian D, same thing, and you'll see that it's streaming, that it was able to connect to the chains, and it's listening and all these things. Cool. And again, we can make sure everything is working by doing npm2 list. This should let us know that all of these services are online. Once you have this, let's get over to the next step, which is actually taking a look at the code that we'll be writing today. All right, let's now navigate over to the EVM Messenger directory. This is in the projects folder right next to Wormhole Local Validator. This is going to be the sample code that we try out. Now, before we get started with actually taking a look at the code, let's go ahead and run the tests in this directory. We can do that by first running npm I to install all of the packages that we need. After all the packages have been installed, we can simply run npm run tests. Now, we'll see what this does is it'll deploy our code to the EVM chains. It's going to register each contract with the other, and we'll talk about why that's important when we look at the code. It's going to then emit a message from each chain saying, hey, hello world from this chain and hello world from that chain. And then it's going to submit each of those messages onto the chains, onto the other chain respectively. So at the end, we should see a hello world and hello world from EVM0 and EVM1 on each chain. And so we'll see that in just a second on the right-hand side here. As you see from EVM0, on EVM0 it says from EVM1, hello world, and on EVM1 it says from EVM0, hello world. So we'll actually go through all the code that makes this possible, but you want to make sure you run a test just to make sure that your environment is set up properly and that everything is working. So the first file we're going to take a look at is the xDapp config. The xDapp config is going to have our deployment info. It's going to have some emitted VAAs that we keep track of. And it's going to also have the Wormhole RPC endpoint. This is the Guardian endpoint where we can fetch the VAAs. Let's go. So you probably want to move the private key and deployment info, deployed address and emitted VAAs into a separate file in production. But for now, we just wanted to keep this all in one nice file just so everyone can see where everything is. This also maintains the RPC endpoints for each of the chains, the Wormhole chain ID for those chains, where the core bridge is deployed, where our contract gets deployed, and then any VAAs that contract has emitted. Every time you run tests, the deployed address will change because it's going to deploy to a different address, and the emitted VAAs will change. Now, one thing you might be wondering is why is the deployed address on EVM0 and EVM1 the same? This is because addresses on Ethereum or on EVM are deterministic. So because we're running on a fresh copy of Ganache on each of these chains, everything we've done on both of these chains has been the exact same. Every block has been the exact same and so on. So when we deploy using the same private key on both chains, and this is the first contract that's deployed, they end up having the same address. This is totally fine, and if you deploy one chain and not the other, you'll see that these addresses change. But if you see that the addresses are the same, that's totally fine. Okay, enough about this file. Let's go into our on-chain code. So under the chains folder, you'll see EVM. We'll only be working with EVM code in this example, so that's the only folder that we care about. But if you had a Solana folder here, you might write some Solana code and so on. For the EVM folder, we're using Foundry. You can check it out at getfoundry.sh to set this up. And if we take a look at messenger.sol, you'll see our messenger file that we're going to go through. The first thing we do in this messenger file is import the Wormhole core bridge interface that looks like this. In your code, you can just copy this from the projects folder and put it in to wherever you are. Next, we hard code in the Wormhole core bridge address. You could of course pass this in the constructor, but I like to hard code this. Next, we're going to instantiate the core bridge by using the interface and the hard coded address. This is pretty simple Solidity stuff. Next, we have a nonce. The nonce is going to be incremented every time we send a message because this is going to be the unique identifier for each message. Now, we'll talk about why this is important when we talk about the stuff that we need to create a message. Next, we're going to have a mapping of UN16 to bytes 32. We call this application contracts. You can also call this emitter contracts. The UN16 is the wormhole chain ID, and the bytes 32 is a wormhole emitter address. And what that means is, say I want to listen to a specific contract on a different chain. For example, I want to listen to the Uniswap contract on Ethereum. I might have in this mapping Ethereum 2, so that would be wormhole ID 2, mapped to the Uniswap address bytes 32. And the reason I might do this is because I want to make sure that no one can forge a VAA and pass it along as if it came from a contract that I didn't actually care about. So this is important to make sure that the VAAs that are being processed by our code actually came from the specific contracts that we want to listen to on other chains. Address owner, this is very standard. This is just, who's the owner of this contract. And then the next is bytes 32 bool mapping completed messages. We take the hash of each message and then we mark it as true if we've processed it, so we don't double process any messages. Let's take a look at some of the functions that we have. First of all, we have the send message function. Now, this is probably one of the simplest functions, but it does a lot. It will call the core bridge publish message with three things: a nonce, a bytes payload, and a consistency level. Let's talk about what each of those arguments means. The nonce, as I mentioned, is the unique identifier for the message. The payload is a bytes payload of unspecified length. Now, while you can submit large VAAs through Wormhole, you might want to be careful if the target chain is someone like Solana, because Solana might have restrictions on how big the VAA can be when it's being submitted. We have more information on this in the docs, and we're working on ways around this alongside Solana. So we'll see if we can come up with better improvements to this. But for now, if you're emitting, for today's example, when we're emitting from one EVM to another, we're just going to care about an unspecified length payload, which is just going to be a string. And then finally, the consistency level. The consistency level is how many blocks the Guardian network should wait before signing the message. So if your code emits a message, user A locked up funds, and we want to wait at least 5 blocks, we might want to do that because the chain that you're on has a 5-block finality. What that means is until 5 blocks have passed, theoretically, someone could reorg the chain. For example, Polygon often reorgs in 50 to 100 block increments, which sometimes loses transactions that have happened in those blocks. Now, if you're doing token transfers, this is actually pretty bad, right? So we want to make sure that we don't create money out of thin air, which if we lock up funds on one chain, mint them on the other, and the chain that we locked up funds on suddenly reorgs, we would lose that money on the sending chain. And then the person who was supposed to have locked up the money would have money both on the sending chain and the receiving chain. So instead of that, we want to make sure that depending on the chain that we're emitting from, we set a high enough consistency level. A high enough number of blocks have to be passed before the Guardian network actually signs the message. Because we're testing, we're just going to set this to 1 because we just want VAAs to be processed quickly. And then finally, we're just going to increment the nonce, which means that a new message has been passed. All right, when we are receiving a VAA, we call the parse and verify VM method and with the bytes payload. The bytes is a VAA. Now we are going to run 3 checks on this. The first is we're going to check that all of the Wormhole Guardians signed this. And we can, again, the parse and verify VM will do this for you. If it's not valid, the reason that the core bridge returns will be used to tell the user why the VAA wasn't valid. Usually one of the signatures is off or something. Next, the second check we're going to do is check if the emitter chain contract is registered. So what that means is, again, as we were talking about the application contracts that we want to listen to, we want to make sure that the VAA originated from a contract on a foreign chain that we actually care about, and it wasn't someone just spoofing a VAA from a different contract. And then finally, we want to make sure that we haven't already processed the message. This is an optional check, the third check, because sometimes you do want to double process messages, or you want to check that the message has been processed in various ways. So the third check is not something that you'll always have to do. Sometimes your business logic might dictate other ways to handle this. And then finally, after all the checks have passed, we just set the current message for this contract to the message that's coming in, which is cast as a string. And again, it's just a bytes payload. The final two functions in this file are getCurrentMessage, which is just returning the current message. And then finally, register application contracts. Register application contracts takes the Wormhole chain ID. So for example, Ethereum here would be 2, Binance Smart Chain would be 4, and not the EVM chain IDs that you might see elsewhere. And then the bytes 32 emitter address. Now, we'll see that we have a lot of Wormhole functions to cast things into Wormhole IDs and Wormhole addresses. But for now, you have to make sure that, basically when you pass in an address to this function, it's not just a 20-byte address on the foreign chain. It's actually left padded and hexified. And again, Wormhole, the SDK, has functions to make this easy for you, but it's just something to keep in mind as you're writing your code. All right, now let's take a look at what is the client for this. Let's pop out of the chains and go to orchestrator.js. All right. Orchestrator.js is kind of like a CLI tool. It's a small client that we're using. Instead of this client, we could also write a front end, but I wanted to make sure that someone who is checking this for the first time has the most simplest code possible to be able to interact with this. If we check the test folder, we'll see how Orchestrator gets called. For example, we call node and then the Orchestrator.js, and then we pass in what chain we want to interact on and what we want it to do. For example, in our test file, we do deploying of both EVM0 and EVM1 contracts. Then we register each chain onto another. Then we send message. Then we submit messages. And then we get the current message. So let's talk about the deploy step first. In Orchestrator.js, if the second argument is deploy, or sorry, if the fourth argument is deploy, fourth argument is deploy, it's going to check that the type is EVM, because depending on the chain type, we want to deploy it differently. And it's going to use Forge, which is, again, we're using Foundry, to actually deploy deploy the code. And here we can see that it's deploying messenger.sol, and it's using the private key and the network RPC that we have outlined in our xDapp config.json, because it's pulling that right here. It's going to grab the config, and then it's going to set the network to whatever the third argument is. In our case, that would be EVM0 for the first line. After it's deployed it, it's going to just do some string manipulation to grab the deployed address and store that. And it's going to set the emitted BAs to empty, because we haven't emitted any BAs from this newly deployed contract yet. And then it's going to write all of that to the xDapp config. And that's it. That's all we have to do in deploy. All right. After that, let's take a look at register chain. So after EVM0 gets deployed and EVM1 gets deployed, we're going to register EVM1 onto EVM0. So to do that, we're going to fetch the config again. We're going to grab the network, that's EVM0, and then the target network, which is EVM1. Make sure that both are actually deployed. And after they're deployed, we're going to get the emitter address from ETH. So the emitter address for ETH is going to be the target network deployed address. That's the ETH address that we see. That's going to generate a emitter address, and then we want to turn that into a bytes. So this is going to return to us a string hex. We feed that into a buffer.from, and that will get us the bytes for the emitter address ETH, and we're going to just store that for a second. Next, we're going to instantiate an Ether's contract using the network private key and network RPC. Then we're going to use the ABI of messenger.sol in the chains folder to create this contract object that we can actually interact with. We're going to attach the signer to it, which is the private key and the RPC node, as we outlined in xDapp config. And then we're just going to call the register application contracts function on Messenger with the target network's wormhole chain ID. So in this case, 4 for Binance Smart Chain, and the emitter address. So again, this is going to be a bytes 32, which we know because it's a buffer.from, and so on. And the wormhole chain ID we can know in the xDapp config. We see that it is wormhole chain ID 4 here for our target network. Cool. Let's go to the next function, which is send message. So send message from EVM 0, it says hello world. And we can go into the same process that we did for register application contract. We grab the network config. We make sure that it's deployed. We connect to the contract on that chain, same process that we did in the previous function. And then we just call send message with a bytes payload, and we just use buffer.from to convert our string into bytes. Pretty simple. Here's where we get the fun stuff right after that. After we've called send message on our contract, it's going to call into the core bridge contract. Remember, if we open up this code, we can see send message calls publish message. That's going to emit a log that the Guardian's going to listen to, and then the Guardian's going to sign it, and then the emitted VAA is going to be ready for us to pick up. So we're going to pick it up by waiting about 5 seconds, grabbing the emitter address, grabbing the sequence number. Remember, we said that the sequence is returned from a unique. The sequence is a unique identifier of a message because it's comprised of the nonce and the emitter address that the core bridge creates. So we're going to grab the emitter address from the ETH, from the contract. We're going to grab the sequence number from the log. And then we're going to go ahead and use fetch to hit the RPC endpoint for Wormhole under v1 sign VAA, pass in the Wormhole chain ID, which in all of this is in the xDapp config, the emitter address, and then the sequence number. If it is not there, we will wait for a little bit, but usually 5 seconds is plenty for it to be there. And if there are no emitted VAAs, we just set the emitted VAAs to the bytes. If there are already emitted VAAs in our xDapp config, we push to the array, and this just writes the new VAA into that list. Cool. So after this is done, if we go to the xDapp config, you see that it has written a VAA to the emitted VAA. So after it calls send message, a VAA gets emitted from core bridge. It gets picked up by guardians, signed by the guardian. We only have the one guardian running, fetched from the guardian endpoint, and stored here under xDapp config. And then we can use this when we actually want to go ahead and submit the VAA. So we're going to submit that VAA from EVM 0 onto EVM 1. The latest here argument just says use the last VAA that's in the xDapp config list. So let's take a look at submit VAA. Submit VAA is simple enough. We do the same stuff that we do before. We grab the current network, the target network. We check the config. We grab the VAA from the xDapp config.json. If we pass in a number, then we're going to grab that index of the VAA. If we want to try to submit, for example, VAA 0 in this list, we would just pass in submit VAA EVM 0, 0. If we wanted to pass in the latest VAA, we just use the word latest. Same thing here. We're connecting to the contract just like we did before. And then we're going to call the receive encoded message. We're going to pass in the VAA bytes now. We're going to pass it in as bytes, but we have it as a base 64 encoded message. So we want to do a buffer.from VAA bytes and then pass in this base 64 so buffer can actually decode it into a set of bytes properly. Okay, so after that's done, we sleep for 10 seconds to make sure everything gets updated, everything's good. And then we can just get the current message, and that's very simple, connecting to the contract and then just calling the get current message function. And that's it. That's our orchestrator. And if you followed along, if you can get all of this code from the EVM Messenger folder, you can check out this example, you can go through the code, you can make improvements. There's tons and tons of areas for improvements in this code, and you can remix it and make it your own. But whenever you're done, hopefully when you run npm run test, you should be able to do this, which is send a message from one EVM chain to another. And that's it. If you followed along this video, not only do you have a Wormhole development environment, but you have some sample code that sends a message from one EVM chain to another. We'll build on this example in the future by sending tokens from one chain to another and using Token Bridge for that, the portal token bridge. And we'll also interact with Solana and Cosmwasm in future videos. So stay tuned and make sure to hit like and subscribe if you enjoyed this video. If you have any problems, we are active on Discord, and you can also ask questions in the YouTube comments below.